Hello, everybody. I know that it's noon time, and I'm the only person standing in the way between you and a lunch. So I'll try to be concise, and hopefully I'll end this talk with some food for thought for you. Before you go to have actual food. Okay, so the topic of my reflective theme presentation is called reinforcement learning for online behavior adaptation in games. Is it still relevant today? So let me just quickly introduce myself. Right, so I'm an assistant professor in computer science at the University of Calgary. The first AIIDE I attended was actually back in 2009, and that's the paper that I'm going to be talking to you about, along with some background, of course. Looking at my research group really focuses on three pillars. So we examine serious games, so games for educational and training purposes. We examine immersive interfaces, so things like VR and XR, and of course, AI is something we're interested in, and specifically reinforcement learning, we look into behavior modeling. Okay, so if you wonder what AIIDE was like back in 2009 and then in the previous years, well, for the longest time, AIIDE was held at Stanford. So Stanford University had all sorts of interesting architecture. And of course, because it was Southern California, palm trees, lots of palm trees. And looking at AIIDE, a lot of interesting social gatherings at AIIDE, a lot of interesting games. Specifically, I think this one that really caught my attention. This is a game called Spy Party. What it caught my attention was if you've never heard of it, it's a game where it's like a reverse Turing test. So instead of the AI pretending to be human, it's actually the human, the player, pretending to be an AI. So that aspect of it really intriguing to me. And finally, back then, StarCraft was actually a big thing. there were big StarCraft competitions where not only you had AI versus AI, you actually had human versus AI competitions with StarCraft, and then people actually sat and watched the competition unfold in real time. And of course, there I was trying to manage two different posters because the author of the other poster couldn't make it, but I'll just leave it like that. Okay, so let's actually get into the actual topic of the theme presentation here. It's online behavior adaptation, right? What is this all about? What do we mean by online behavior adaptation? So we're really talking about, these NPCs in games where you have a system or methodology that enables the NPCs to be able to dynamically adjust their behaviors in real time, to adjust to actions for the player or changes in an environment or some evolving in-game context, right? So as things are changing, are your NPCs able to adapt to them? Are they able to adjust their behavior to adapt to whatever is changing? Because then if we want to have realistic behavior, if we want to have believable behaviors for our NPCs, then they should be able to adapt to changes quickly, right? So we want these NPCs to have enhanced realism, challenge, and engagement in our video games. Okay, so if you wonder, well, back then, what was the state of the art at the time, right? So no LLMs, definitely no. Were there deep neural networks? Well, the concept of neural networks existed back then, of course. The concept of neural network existed for the longest time. But practically speaking, back then, we really didn't have the hardware, the technology in place to deploy deep neural networks in practical applications. So we really didn't have those tools available at the time. So what did we have available at the time? Well, here are just some examples, right? So there were a lot of what we call cheating NPC behaviors in that they're not real behaviors. So for example, in Grand Theft Auto, what you have is that you have these NPCs, they just get spawned off screen whenever they need it, and then you see them walk across the screen, and then they turn into a corner off the screen, and then they get despawned. So they don't really exist in this virtual world. They're just props being used whenever needed, right? So that's not really believable NPC behavior, but at the time, a lot of that was that. So there were also finite state machines, which eventually turned into behavior trees. You know, so you define these states. Well, a programmer or a game designer define these states and then define this transition between states and use that as the control mechanism for the behaviors. And of course, an obligatory slide. It seems that there's an unwritten rule here that whenever we give these presentations, we have to mention facade at some point. So here you go. This is actually a screenshot of a presentation I gave back in 2009 talking about facade, right? So there's beats, there's drama manager, and we know that the game was really fancy for its time, but for the amount of effort that went into the game only had 2 NPCs. So it's really not scalable when you have a game with more complex settings. So a lot of the NPC behaviors back then were rule-based, where rules were created manually. So that involved a lot of scripting. When we say scripting, we mean coding, right? Manually created by a game designer, and that created a lot of frustration. So with that being said, we really want to have some sort of behavior learning mechanism where we want these NPCs to be able to choose reasonable actions and to be able to learn from their past experience and adapt to the environment. So what could we have done back then? One of the things that existed was something called dynamic scripting, which was actually proposed back in 2006, but also there was a talk at AIIDE 2007, where the idea here is that you have these rules that control your behavior, but those rules are manually created. But what you have is that you create a rule base, basically a database of rules, and then upon every encounter, you have scripts that are generated dynamically from the rule base. Basically, you have a script that picks inside your rule base, picks the rules, puts them into a certain order, and then use the generated rules to direct the behaviors of the NPCs. And at the end of every encounter, you would essentially get feedback on how those rules did. You would then adjust the rules according to the feedback caused by the actions. So that's called dynamic scripting. And then it was shown in a control setting in the game Neverwinter Nights, and really old game now, where you have teams of essentially NPCs, and then they essentially compete with each other in a combat scenario. So they fight each other, and then whoever wins wins whoever lives at the end wins the comeback. So in this sort of control scenario, it's really easy to tell whether your behavior is good or not, because if you live, it's good. If you die, then it's not good, right? So, and then the year after that, in 2008, there was a talk using essentially SARSA-based reinforcement learning. There was an algorithm called AIIDE, which is based on SARSA, a reinforcement learning technique. So in reinforcement learning, you define set of states, set of actions, and you choose actions based on the action value function, which is a Q function, QSA function. And then based on reinforcement learning, you would update the QSA value with the reward that you receive each time, your standard reinforcement learning, right? So, and what AIIDE, this algorithm proposed was that it proposed separate learning rates for each action. So every action has its own learning rate. And then these learning rates are adaptive based on the environment, based on how stable the learning environment was. And then also there was an adaptive exploration rate based on the outcome of learning. So basically, if you are doing well, then learning gets slowed down. If you're not doing well, that means you are not choosing the correct actions, so your learning gets faster. So that's the idea here. Okay, so with that paper, they again implemented the algorithm in this combat scenario just to see how it performed. And I could just show you that's what the scenario looked like inside the game Neverwinter Nights, where you got teams of players competing with each other just to see how good the algorithm did, right? So as a comparison between the reinforcement learning based algorithm versus the dynamic scripting, which was in some sense also a type of reinforcement learning. But if you compare them, you'll see that the starter-based reinforcement learning had just a little bit of an advantage. So if you look at the win percentage graph here, based on how much alert is winning over DSP, you will see that the win percentage is somewhat above 50%, meaning that it has a little advantage, but not by much. So this is the background. Okay, so when I first started my master's, I examined everything that's done before because, of course, we all stand on the shoulders of giants. So I examined the work that's done before, and I was looking into why the reinforcement learning technique was not doing as well as I had hoped. Well, I found that there was really a need to model the agents, because in a lot of these environments, the action that you take, how good the action is going to be, it really depends on what the opponent's doing, because you're taking an action, the opponent's also taking an action at the same time. Everything is real time. So if you take an action that is negated by the action of the opponent, then the action actually not going to be good. So you really need to model the opponent agent. And if we're talking about teams, then you probably want to model what your teammate's doing as well. So that's what I looked into. Basically, we need to keep track of the opponent's actions. We need to keep track of states, of your past states and the opponent's past states. So in 2009, I came to AIIDE and I presented this work, which is a reinforcement learning technique augmented with what I call agent modeling. So in addition to the set of actions, the set of states, we also keep track of set of the opponent agent's actions. So we want to essentially model what the opponent is doing. And our action value function in our reinforcement learning is using this agent model to assign values to the actions. Now, at the big picture, at each step of your reinforcement learning, we're going to increase the frequency of the current state. So we're keeping track of what the states that's happening. You're going to increase the frequency of the current state. You're going to increase the frequency of the current opponent action in the current state. So we want to keep track what the opponent has done in each of the states. And we're going to choose the next action. And the next action that we choose is going to be influenced by the weighted average of the values of the opponent actions. So we essentially keep track of the opponent actions, what they have done in the past, and we're going to use that to essentially make some of the prediction what the opponent is going to do next. And the action that we choose is going to be dependent on what we think the opponent is going to do next, right? So we want to pick an action that essentially is a counter to what the opponent is trying to do. So that was the idea of our agent model here. So with agent modeling in place, what we see here is that looking at the win percentages, you see that win percentage now increased a bit from the model without opponent modeling, without agent modeling. That at the end of the 500 episodes that we've tested, you see that it's winning about 70%. We tested with different settings. So this one is just with sorcerers fighting each other. We tested with different settings with a mix of fighters and sorcerers, and we still see the advantage of our methods. We compared our technique with agent modeling versus the technique without agent modeling, and we see the advantages with the agent modeling. Again, it's winning at around 60 to 70% of the time. Again, testing it with different compositions of your agents to see if there's still an advantage. And most importantly, I want to show you this graph here because we're talking about online behavior adaptation, right? So this graph shows you that the environment changes at 500 episodes. So what happens here? What happens here is that we have teams of sorcerers competing with each other. At the first 500 episodes, there's a certain setting for the type of magical spells that the sorcerer can use. Right at episode 500, we swap the environment. So now that the spells that the sorcerer could use are different. So they are no longer able to use the previous spells, and the spells have different effects, right? So now immediately it throws everything into chaos, and you have to adjust to the environment. So what we can see here is that with agent modeling, with this reinforcement learning technique, you are at 500 episodes to 550, you see the win rate drops down to 50% because now everybody is trying to adjust. But then soon after that, our techniques adjust to the new environment, and then it gets back to winning about 80% of the time, right? So you see that the rapid online adjustments based on changes in the environment. So and this is what we want to see in an online adaptive behavior. Okay, so moving on from that, we're not really satisfied with just combat because in these games there are a lot of different scenarios than just combat, and different players prefer different things. Some players, well, they're not really big on combat. Maybe they prefer other types of gameplay, like storytelling or working with working in a collaborative environment. So one of the other things we've checked is our technique able to work with a player's companion, right? A companion is an AI-controlled NPC who's there to help you. So in this next one, which is the year after, we essentially examine how we can use this reinforcement learning technique to apply behavior to a player's companion AI. And there are really two things we've added. One is called greedy epsilon softmax action selection. So you're going to select the action with the highest QSA value with probability 1 minus epsilon, which is standard reinforcement learning. But we're going to use softmax with probability epsilon, excluding the best action, for sort of exploration. So we give exploration instead of random exploration, we give it some indication of using softmax so that it actually prefers certain actions over others. And the second thing we did is we essentially applied what's called double rewards per step, where one reward comes from the environment and the other reward could come from the player, because now you have a player and a companion, and the player may provide some feedback to the companion on whether what they're doing is good or not. So we want to take that into account as a double reward system. Okay, so when we talk about companion NPCs, one of the things we really want to look into is whether we can have these believable NPCs that are essentially self-preserving. Because a lot of games, you have these companions that are essentially mindless drones that will do whatever the player character tells them to do, with little regard to their own safety. But that may not appear as realistic. So we want to see if we can have this sort of self-preserving companion behavior where sometimes they will refuse the player character's command because it's going to cause themselves harm, right? So what we examine is that it's a scenario where there are traps you have to disarm, because in many role-playing games, you're going to encounter traps, and the player character can order their companions to help them disarm traps. Assuming the companion is like a rogue type character when they can detect traps better than your player character, right? So in this example here, your companion is there to disarm the trap that is in front of the player character. The other thing the companion can do is mark the trap without disarming it, which is a safer action, because if you try to disarm a trap and some traps are too hard to disarm, the trap will go off and hurt you. So if you just mark it, that's a safer action to take. Or you can just inform the player character, hey, I think there's a trap somewhere over there, but it's too dangerous, I'm not going to touch it. So that's an action your companion can do as well. And finally, your companion can just do nothing for reasons. All right, I'll show you now. Okay, so now we have some experimental results I can show you here. So we built this environment in which you are in this dungeon here. You're going to encounter 10 easy traps, 10 medium traps, and then 10 hard traps, right? So easy traps are easy. You can disarm it, usually with little harm to yourself. Medium traps are a little bit harder. There's a higher probability that you could fail in your disarming and they will hurt you. And the hard traps are really hard to disarm. So there's a high probability you could fail and hurt yourself. And then we have an approval system for our companions. And the approval system is actually dependent on whether your player is a supportive player or not. If a player is a supportive player, so if your player actually cares about the companion, you'll see that the companion's approval goes up because of the player is being supportive, it's giving supportive feedback. You can have a selfish player who doesn't care about the companion and just orders the companions to disarm traps regardless how difficult it is. So in this case, you see that the companion's approval rating drops quickly once they encounter hard traps that could hurt the companion. Now, the interesting behavior that I want to show you is this one here. So this is the graph that's showing you the state action value, the Q values of the different actions that the companion has learned. So if the player is a supportive player, we'll see that looking at the actions, the disarm action at the beginning has high values, meaning that the companion is willing to disarm the traps. But once we encounter the hard traps at the end, you'll see that the disarm value goes down, but the value for mark goes up, meaning that the companion now is willing to mark the trap to help the player character, but also not disarming and hurt themselves, right? But the companion is still willing to help because the player has been supportive. On the other hand, if you have a selfish player, so the player is always order the companion disarm regardless of how difficult it is, what you see here is that, well, at the beginning, for easy traps, the companion is still willing to help. For medium traps, but once you encounter the hard traps, you see the value for disarm goes down rapidly, and the action that has the highest value, so that the action the companion has learned to do is actually the one that does nothing. So the companion will say, I'm not gonna do anything, I won't say anything, go ahead and hurt yourself. Why? Because the companion has learned that this is a selfish player. If the companion actually informs the player or let the player know, the player will force the companion to disarm. So the best thing to do is just do nothing and just stand back and watch the player hurt themselves, right? So we can see that now the companion has organically learned the action that actually preserves themselves in the situation, depending on the player's response to the companion. Okay, so that's really what I want to discuss in terms of what happened back then. So what has happened since then, right? Now, a lot of things has happened since then. So this is really a I don't have a lot of time to go into details on everything that's happened since then. But one of the things I want to mention here is that, well, as most of you probably know, that there's something called deep learning. And as you can see this graph from Google Trends, that deep learning shot up in some years after that, and then everybody jumped onto the wagon of deep learning, and then that's that. Now, obviously, deep learning has solved a lot of problems, including deep learning with reinforcement learning. It gives you deep reinforcement learning. But what we see is with any sort of deep neural network or deep learning, it requires a long training time, right? So you really no longer have this ability to deploy sort of techniques and have them adjust in real time based on some changes in your environment, that's a little bit disappointing, right? Because you no longer have the ability to deploy this sort of technique for the purpose of online behavior adaptation. But what we have seen here is that other techniques kind of fill that space. We've seen a lot of works after that deploy search-based techniques. So in particular, multicolor tree search, UCT, we've seen a lot of work that deploy UCT and multicolor tree search for the purpose of online behavior adaptation. So I think that's an interesting area to look into. And even nowadays, MCTS still being used by a lot of applications, including some talks in this year's AIIDE. So really the question here is, are we happy with the current state? Right? I think online adaptation of your behavior is important, right? Because in video games you want to see online adaptation. You don't want to have a deep learning technique where you have to train for like 1,000,000 steps before you see an actual behavior change. That's that has its purpose, but in some applications you want to have that real-time adaptation. So I think it's an open question. I think there's a lot to think about, right? Like what exactly can we do? Like, are we happy with what we have so far, or are there other further topics of research that we could look into that can provide better online adaptation? So I will leave it as a food for thought for you, something that I'll be happy to discuss afterwards. Okay, so that's the end of my theme presentation. Thank you. Some references that I've talked about, credits for the slides, and then I'll be happy to answer any further questions. Thank you.